All right, this is AP Calculus ABA, Unit 3, Lesson 4. We're talking about continuity and discontinuity. Let me give you an intuitive idea of continuity, and then we'll give you the formal definition and kind of explain how it works. Informally, continuity means this. You can draw it without picking up your pencil. Okay, so draw it from left to right, sketch it without picking up your pencil. So if I have some function that does this, that's a discontinuity. Okay, that's a discontinuity. Particularly, this is called a jump discontinuity. Likewise, if I have something like this that we've experienced before, we have an asymptote. This is an infinite discontinuity. And if I've got a hole, it could be just a hole, or it could be a hole with a function value sitting outside. This is called a removable discontinuity. Together, these discontinuities are called non-removable. The idea of being a removable discontinuity could be plugged by simply changing the function value and filling the hole. But these aren't as simple as filling a hole. There's a gap, there's a jump, there's a leap. Okay? And so if a function goes from left to right, and it has no jumps or gaps or holes, it is said to be continuous. Okay, now that's the intuitive idea of it. So let's go into the formal definition. Okay, a function is continuous. F of x is continuous if and only if, so this flows both directions. It's continuous if this is true, and if this is true, it's continuous. For every number c in the domain, every c in the domain, the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x. You may recall that's the definition of a two-sided limit, but we're going to add one more thing, equals f of c. So we're also going to plug the hole. Remember, limits don't care what the function value is at c, just what it does as it approaches c. But for it to be continuous, we need the function value also to match the limit from the left and the right. So for every c in the domain. Okay? Now, this is a little bit different if we're talking about continuity on an interval. Okay? On an interval, it changes a little bit. On an interval, okay, let's say, for example, I've got some function that goes between 2 points. There's f of x. We can say f of x is continuous from a to b if for every point c between a and b, for all c between a and b, okay, a and b, the previous rule applies. The limit of as x approaches c from the left equals the limit as x approaches c from the right equals f of c. Okay, for all c, all numbers between a and b. And for a, the limit as x approaches a from the right of f of x equals f of a. And For b, the limit as x approaches b from the left of f of x equals f of c. So gone is the requirement that it be a double-sided limit for the points a and b. And that makes sense if you think about it, right? It's continuous if, as I approach from the right, there are no gaps. We don't care if there are gaps on the left because it's just over a set domain from a on. And again, on the right-hand side, we only care about the left-hand limit, right? So we only care as we approach from the left and the function value itself. So that's the exception for a closed interval, okay, on an interval from a to b inclusive. Okay. By the way, we can't really talk about an open interval. Okay, it can't be closed on an open interval because it doesn't include the function value. And that's an interesting exception. All right, so that said, I want to introduce the intermediate value theorem because that's brought up here in this lesson. Intermediate value theorem is a very important theorem in calculus. Okay, and oftentimes you'll see it just shorted to IVT, intermediate value theorem. Intermediate value theorem. And what this is it's a rule that applies for all continuous functions. So for f of x continuous, on a to b, right? For f of x continuous on a to b, let's draw a sketch here. So we have some function f going from a to b. Right? And this is f of x. Okay? For f of x. Okay? For f of x continuous on a to b, right, there exists some c between a and b, or some c on the interval, or we'll say in the member of the subset ab. Some c on the interval a to b, okay, such that or actually, there exists. I'm going to say something else here. Given L between f of a and f of b. So we have some L value, right? That's between a and b. And what we're saying is there exists some c on the interval a and b such that f of c equals L. Okay. Now let's put that into more complete context here. All right. Let's say we give it some numbers. Let's say a is 1. And f of 1 is, well, 1, 2, 3. Okay? And 1, 2, 3, 4, 5, 6, 7. Let's say this is 8. Okay? And this is 8 and 1, 2, 3, 4, 5. Okay? What this is saying is there is some function value, some f of c, some value c, such that, and the c's got to be between a and b, such that f of c is L. And in this case, it looks like it's like 6. Okay? And so there is some function value c that gives me a function value between 3 and 5, between the outputs, right? Between f of a and f of b. This is really important when we want to find something called zeros, right? Okay? let's say, for example, here, we've got a function, right? And we've got a graph. Let me draw the graph. I'm going to draw the x-axis. Okay, x-axis. All right, and let's say we've got a function value a, and f of a is 3, and another value b, and f of b is -4. Okay, f of b is -4. Okay, here's what the intermediate value theorem says, special case of it. If f of x is continuous, that means it can be drawn without picking up your pencil, right? Without picking up your pencil. There must be a value c between a and b such that f of c is 0. Okay? In other words, that's something called the X-intercept. There has to be an X-intercept or a 0 in there. And oftentimes in algebra and mathematics, we're looking for zeros. So here's the point. To get from f of a to f of b, without picking up my pencil and without going outside the bounds, I can't go outside a and b, I've got to go between a and b, somewhere in there, in order to get to f of b, I have to have crossed over the line x, right? And this is c, and this is the point c0. So the output must be 0 at some point. And that's logical if you think about it, right? There must be some value between a and b that gives me a 0 of the function f. All right, so that's kind of the idea of the intermediate value theorem. That applies, of course, in the previous example to other values other than c's, like 6. So if I have f of 1 is 3 and f of 8 is 5, then there exists some c, some value c between a and b such that the output is 6, right? And think about it. It makes a lot of sense if you consider it. All right, let me know if you need help.